Alrighty guys, let's take a look at another problem here. This says in a simulated car crash, Mr. Shermack acts as a crash test dummy. His BMW, with a mass of 1,750 kilograms, is traveling 30 meters per second, so that's my initial velocity, at ground level of a height of 0. He crashes his beautiful orange car into a huge spring attached to a wall. Assume that 99,000 joules of thermal energy, so it basically tells you that this is thermal, help bring the BMW to rest. And the rest of the energy at the end consists of elastic potential energy. The spring constant we know is K, is 4,550 newtons per meter. How much energy does Mr. Shermack have at each point? All right, so let's start with a picture. And here's our picture of the car. And initially, this car is driving at a velocity of 30 meters per second, and it has a height of 0. Therefore, the only energy that we're going to start with is going to be kinetic energy because it has no height and the spring constant is not stretched. So in the beginning, x is 0. And again, there's no thermal in the beginning because we don't have thermal to begin with. So all we're doing is starting with kinetic energy. We know that kinetic energy is equal to 1/2 mv squared. We said the mass of Mr. Shermack's car is 1,750, and we said that the initial velocity of his car is 30 meters per second. So all we have to do is take these numbers and plug it into our equation. Kinetic energy is equal to 1/2 the mass, 1,750, times the velocity squared, so 30 squared. Doing so, we should get a kinetic energy of 787,500 joules. Go ahead and take that and add that to our table up above, 787,500. All right, so that energy is our total energy, which is super important because we're going to need that in order to figure out the later parts of what's missing. So at the end, the spring compresses. So here's his car, and then at the end, he hits some spring at the end. And the spring has now compressed some distance, x. We don't know how far, we just know that it's compressed some distance. GPE still depends on height, and there's still no height because he's driving on the ground, so this is 0. At the end, his car comes to a stop. It tells us right here, comes to rest. So the final velocity should be 0, meaning that our kinetic energy in this instance should also be 0. So remember, the final velocity is 0, therefore the kinetic energy is 0. It tells us that he loses 99,000 joules of energy to thermal, and then some energy is left over to EPE. So this is where that total is going to come into play, because our total energy that we started with was 787,500 joules, and that should be the same that we end with. And we know that we get the total from adding everything up. So this plus this plus this plus this should equal our total. Same with down here. Those two are 0, so that means that EPE plus thermal should give us that. So in order to figure out the missing EPE, we're just going to write that down here. We have EPE plus thermal is equal to our total. And for this problem, we're trying to solve for EPE, so I'm going to subtract thermal over to the other side. So I get EPE is equal to my total minus my thermal. And now I just go ahead and plug my numbers in. So EPE should be equal to the total, which is 787,500 joules, minus the thermal, which is 99,000 joules. If we do the math here, we should find out that our EPE should be 688,500 joules. Now I can go ahead and take that number and add that back into my table up here, 688,500. Next, it wants me to figure out how far the spring compresses. So the spring compressing is at the end. So I'm going to use my EPE equation because that's the one that's going to have the distance that it compresses. We know that EPE is equal to half kx, where x is the distance that it compresses. And by half kx, I forgot to mention the squared, but half kx squared. So all we need to do is manipulate this to solve for x. So let's do that first. Let's multiply by 2, divide by k. So we get 2 times our elastic potential energy, EPE, I'll put that in parentheses so we know it's just one term, divided by K is equal to x squared. And then again, we're solving for x. So to do that, we need to square root both sides. So all we need to do now is plug this into our calculator and get a number. After we plug it in, we find out that the distance it compresses should be about 17.4 meters. Now that we have the distance compressed, well, let's think about this for a sec. It says, how far does the spring compress in stopping the car? It depends what we consider to be our positive or negative distance. I would argue that a compressed distance would be negative, but we never set our origin. So unfortunately, we don't know if it should be positive or negative in this case, but I again would make the argument that compressions are negative and pulling it would be positive, or stretching are positive. Lastly, it says, what is the final speed of the car? Well, it tells us in the problem, it says the car comes to rest, so the final speed is just 0 meters per second.